Hi guys! Welcome to another Solve Reactions with Me video. Today we're gonna solve these 4 reactions from a real organic chemistry exam that I had back in the days. In the first reaction, on the left side, we see alkyne and combination of sodium with liquid ammonia, which is usually used to partially reduce an alkyne to alkene. So basically our triple bond will be converted into a double bond. This reaction is quite simple. However, there is a very important detail. As a product, we get here a transalkene or E-alkene, depending on the substituents hanging around the double bond. In our special case, when we add 2 hydrogen atoms to the triple bond, we actually don't see if the product is cis or trans, because anyway it has 2 hydrogen atoms on the right carbon. But I'm showing here the new coming hydrogen atoms in green, so that you explicitly see that the product would have a trans configuration if there was any other residue on the right carbon. Okay, now, why does this reaction lead to a trans configuration in the end? Let's take a look on the reaction mechanism. Probably you already know that metals can easily give up their electrons to form stable cations. In the case of sodium, it can easily donate 1 electron so that the alkyne turns into an anion radical. Imagine it in this way. The bond between 2 carbons is basically just a pair of electrons. So when you add another electron to this pair, one of the carbons will end up with the full pair of electrons and negative charge, and the other carbon will carry a single free electron, which makes it a radical. Also notice that the negative charge is on the less substituted carbon, because an electron-donating group like CH3 would otherwise increase the electron density around the negative charge and destabilize the molecule. And at this point you can already see why our product will have a trans configuration in the end. The lone electron pair and the single electron are positioned in the way to reduce their electric repulsion as much as possible. Now, since we have a negative charge on the carbon, the compound acts as a base. Negatively charged carbon attacks the partially positively charged hydrogen. And as a result, we get an alkene radical and the amide anion. This amide anion finds the sodium cation that was produced before, and they neutralize each other. Next, we have a repetition of previous steps. Our newly formed radical takes another electron from the next sodium atom, turns again into an anion, and this anion takes another hydrogen from liquid ammonia. Negatively charged carbon attacks the partially positively charged hydrogen, and as a result we get a neutral alkene as the main product and the amide anion. The amide anion finds again the sodium cation from the previous step, and they neutralize each other. Now let's take a look on the second reaction. Here we see again an alkyne on the left side. It has a triple bond, namely 1 sigma bond and 2 pi bonds. The most typical reaction type for alkynes is an addition, and in many cases it is electrophilic addition, because positively charged electrophiles get easily attracted to the electron-dense triple bond. But here is one important thing. Electrophilic additions on alkenes and alkynes usually follow the Markovnikov rule. So normally you would just add the hydrogen of the HBr to the less substituted carbon and the bromine to the more substituted carbon. But here we see peroxide as another reagent, and this is a good hint on the radical mechanism of the reaction, because peroxides can very easily form radicals. And what is special about the radical mechanism is that the radical addition does not follow the Markovnikov rule, and I will show you why. So let's take an absolutely random peroxide. Peroxides can form radicals very easily. Sometimes it is enough to just provide some sunlight energy for this to happen. This reaction step is called initiation step, where we form the first radical, our radical starter, so to say. Now we enter the propagation step. The radical starter takes away the hydrogen atom from HBr and generates a bromine radical. This bromine radical attacks our alkyne molecule, and theoretically bromine could form a new bond with the left or with the right carbon atom. However, if it binds the left carbon, a primary radical would be formed, and we know that primary radicals are less stable than secondary and tertiary radicals. That is why bromine binds only the right carbon atom, so that a secondary radical is formed. Another thing is also very important. This radical can take a cis, or in our case Z configuration, as well as a trans, or in our case E configuration, with almost the same probability. That is why two different radicals are formed. And now each of them reacts with HBr, takes the hydrogen atom, and leaves a bromine radical. This is the end of the propagation step. Our main reaction products are formed, and in the termination step, all radical species that we had on the way will bind each other and form a bunch of different molecules, like for example bromine gas or alkene dimers. Okay, so the final solution here is the mixture of Z and E alkenes. It is also very important to mention that this solution is valid only for the case when you have only one equivalent of HBr, meaning one molecule HBr per alkyne molecule. If you have more HBr in the system, of course it will react again with alkenes, because we still have a double bond that can be easily broken again with a radical. Now let's go to the third reaction. On the left side we have alkyl iodide. And in general, alkyl halides react with magnesium in the way that magnesium inserts itself between the carbon and the halogen. So in the first step, magnesium inserts itself between the cyclohexane and the iodine. And the formed compound here is called Grignard reagent. Now let's take a look on the reaction mechanism. You already know that metals in general can easily give away their electrons and turn into cations. And exactly this is happening here. Magnesium is giving one of its electrons to the alkyl iodide, so it turns into an anion radical. And magnesium is now positively charged. The bond between carbon and iodine breaks, leaving one electron of this bond on the cyclohexane and another electron on the iodine. So we have now a cyclohexyl radical and iodide anion. And we still have a magnesium cation radical from the previous step. So in the next step, magnesium and cyclohexyl radicals connect their unpaired electrons and form a new bond. Since magnesium also has a positive charge, it attracts the iodide anion, and finally we get the final Grignard reagent molecule. As you remember, we had deuterium water as the second reagent, so in the second step, hydrolysis of Grignard reagent happens. I will write down the D2O in this form, as we usually do it for HOH, so it is easier to see what exactly happens next. The partially negatively charged carbon attacks the partially positively charged deuterium of D2O, so that a new bond between carbon and deuterium is formed. And our main final product is a monodeutyrated cyclohexane. As a byproduct, we have a deuterated hydroxymagnesium iodide. Let's write down the final solution and go over to our final reaction for today. Once again, we have an alkyne, and another important feature you need to know about alkynes is that this proton at the triple bond can be very easily cleaved, because the bond here is very polarized. It is even said that this proton is acidic, because it can be so easily cleaved. And the combination of reagents here tells us that we have an alkyne chain elongation reaction. First, when we add sodium amide, the partially positively charged proton is attacked by a nucleophilic amide anion, so that this acidic proton gets substituted by sodium. Our alkyne now has a lone electron pair on the carbon and it carries a negative charge that is neutralized by sodium cation. The amide anion with the proton gives us ammonia as a byproduct. And now this sodium salt can react with alkyl bromide. Our alkyne anion acts as a nucleophile and attacks the partially positively charged carbon. So as a result, we indeed elongated our alkyne chain and sodium bromide is left as a byproduct. Okay guys, that's it for today. I hope this video was helpful for you. Let me know in the comments below if you have any questions or if you have any reactions on your mind that you want to solve with me next time. See you in the next video. Bye!